So the mathematical tool or notation or ideas that we need, again, gradients and Hessians. Somehow we need to apply gradient and Hessian and do some analysis on them so that we may get our desired convexity. So I hope gradients and Hessians are not too weird for you, because you actually should have known them if you have applied gradient descent and the Newton's method. Okay, so it's simply a collection of first order derivatives and also a collection of second order derivatives. Okay, so in this case, pretty much what we need to do is that we need to do some analysis on these functions or these quantities, and we somehow need to have them satisfy some properties so that our function is convex. One thing to remind you is that all our Hessians, at least in this course and in most of the practical problems, it would be symmetric, because we can see that this and that, these two values are doing second order derivatives with x1 and then with x2. So it doesn't really matter what the order is if we are talking about continuous second order derivatives, right? So I hope this makes sense to you. Okay, so this is just a numerical example to help you to recall your memory about how to do the gradients and the Hessian calculations. So for this particular function, the second or the first order derivatives can be collected to obtain your gradient, which is a vector. And then for Hessian, you collect all your second order derivatives, and then you get this particular matrix. So the gradient and Hessian somehow are functions of variables. Okay, so you may see that they may not have a single value when they are at different points. So you may specify a specific point and ask what's the gradient at that point, what's the Hessian at that point. Then all you need to do is to plug in those values into your functions. Okay, so if we are talking about 3, 2, and 1, then in this case, this would be 6, this would be 1, and this would be 2 plus 3. All right, so your gradient would be 6, 1, and 5. So for Hessian, pretty much everything the same. It's just that here you need to plug in 1. So your corner value would be 6. That's the Hessian at the point 3, 2, and 1. So now we are ready to talk about our convexity condition. So first, let's recall the following theorem for single variate functions. Okay, we say f is convex if the second order derivatives are non-negative. It's an interior local mean only if the local the first order derivative is 0, and then finally is convex. If it is convex, then it is a global mean if and only if the first order derivative is 0. So now we have an analogous theorem for multivariate functions. Okay, so f would be convex if the Hessian matrix obviously is some kind of second order derivatives. All right, so our Hessian matrix should be positive semi-definite, which is something that we will tell you in the next page. And then if we have that condition, our next one would be our x bar would be an interior local mean only if the first order condition is satisfied, only if our gradient is 0, which is again another extension from 1 dimension to n dimensions. And then finally, if f is convex, our x star would be a global mean if and only if the gradient is 0, again the first order derivative. So the only thing that needs some illustration is the idea of positive semi-definite. So let's take a look at what's that. Positive semi-definiteness is a property of matrices. So the definition is here. A symmetric matrix A is called positive semi-definite if for any vector x that is in Rn, we have this property. So that property says x transpose Ax are all non-negative for any possible x that you may find. So pretty much this is some kind of extension of the second order derivatives being 0. So what does that mean? Well, pretty much if your a is a scalar, then this somehow gives you x squared, right? So that has something to do with second order derivatives. But anyway, let's take a look at these examples. So the example says that if you have an a which is 2, 1, 1, 2, then if you take any possible x, so your x obviously are x1, x2, okay? And then if you do this, you're going to get x1, x2 multiplied by 2, 1, 1, 2 multiplied by x1, x2, okay? If you do some arithmetics, you would get this one. And this one may be further arranged to sum of several square terms. That's all non-negative. So that's how our A matrix here is positive semi-definite. Okay? So that's one successful story. But on the other hand, if your A in the second example is 1, 2, 2, 1, then in that case, after you do this x transpose Ax, you get something different. And you may see that if you plug in 1 and a negative 1, that's going to give you a negative number. So it does not satisfy the definition, and then it is not positive semi-definite. Okay. So the thing is that a function is, a matrix is positive semi-definite. Somehow that has something to do with convexity, right? Previously we say f is convex if the Hessian of f is positive semi-definite. So being able to show that a Hessian is positive semi-definite is actually very useful. So how do we do that? That definition may be too difficult to be applied. So what we will do is actually to use the following proposition. So all the following statements are equivalent. What's that? So your A is positive semi-definite, or A's eigenvalues are all non-negative, or A's leading principal minors are all non-negative. So if you recall your memory from linear algebra, A's eigenvalues, if we denote it as lambda, has something to do with the eigenvectors. They would together satisfy the equation Ax equals lambda x. Okay? So if you are not familiar with this one, I need to ask you to help yourself to understand or to review or to learn linear algebra by yourself. But this is just one way to check the property of A. So that's fine. Another thing is leading principal minors. Okay? So if you have a matrix, the matrix has several submatrices. For all those upper left k by k submatrix, if k is 1 is this number, if k is 2, that's formed by these 4 numbers, if k is 3, that's a 3 by 3 matrix, and so on and so on. The kth leading principal minor would be the determinant of that corresponding submatrix. Okay? So in that case, if A's leading principal minors are all non-negative, you may still say that, oh, okay, A would be positive semi-definite. So I'm not going to prove this proposition because this belongs to the area, to the field, to the sub-scope of linear algebra. We will take it as given, and later we will show you some examples about how to do the calculations to do the check. So our general procedure would be, given a function f, what we will do, first find its Hessian. This is necessary. And then either find all its eigenvalues or find all the leading principal minors. And then determine whether the Hessian is positive semi-definite, or find a region over which the Hessian is positive semi-definite. And then we may say, oh, okay, over that region, our function is convex. and then we may see how that helps to solve some problems.